Okay, number 53, we have a weak acid in the beaker and a strong base being added to it. So we start out at 0 milliliters of base. We only have acid in the beaker and water. It's a weak one, so we have to ice. And when you finish icing, don't forget neglect, because 5%, you solve for x, negative log of x is the pH, and you should rate assumption good here. Okay, so that's the initial. At 50 milliliters, I know I didn't make you do this, but what we have in the beaker is the acid and the base and water and the conjugate base. So we take the molarity of the acid times the moles, times the liters to get the moles, and molarity of the base being added times the liters to get the moles there. We will subtract away all of the base, and notice that it adds over to the right side. In the strong curve, we don't care about the conjugate, but in the weak strong curve, we do, because this weak one will affect the pH of the solution. Okay, so we have to watch out for it because it's going to trick us up. Okay, so we divide by the total liters, and you can ice. Okay, and we would lose x here, and we gain x here and lose x from the acid side. We would, of course, neglect those x's, and we would end up with this expression and the negative log, solve for h, and we would get the negative log, and then we get 4.26. Alternatively, you can just use an equation. This is the Henderson-Hasselbalch equation. pH equals pKa plus the log of the anion over the full acid. Okay, so we use these numbers here, and when you do that, you also get this same number. Notice that it's slightly less than the pKa. pKa would be when these two things, the anion and the cation, are equal. This one's less because we have some more acid in there, so it's going to pull down the pH right now. Okay, the next part is actually turns out to be halfway. I know it's halfway for two reasons. If I look back at the original problem, we had 0.2 molar being titrated with 0.1. So if I have 100 milliliters in the beaker, when I add 100 milliliters of the base, that would be halfway. I would need 200 to reach equivalence because this is half as strong as what's in the beaker. I also know it's halfway because when I Becca to the bottom, sorry, these should be 2's. The acid and its conjugate base are equal, and that happens at halfway always. The base will go away, and also I know that it's half. When we say halfway, half of the moles of acid that was in there is left over, so 0.02 divided by 2 is 0.01. So we have these molarities. You can either ice, so icing would get you this, the Ka and the top and bottom would cancel, and we would find H plus equals Ka or pH equals pKa. Henderson-Hasselbalch would get you pH equals pKa plus the log of the same number on top of each other would be the log of 1. So we're adding 0, so pH equals pKa as well. That's halfway. At equivalence, we have the acid and the base being added, and this side, everything goes down to a 0. That's how we know it's equivalence, because the base being added equals the moles of acid that's in there. Everything adds to the other side. So we have kind of a tricky thing happening to calculate the pH here. We actually only have right now in the beaker C2H3O2 minus and water. So when I think about what's going to happen here, I know that this is the conjugate base. So it's going to make OH minus and its conjugate acid. That's how I know to write this equation, because all of this stuff is not in the beaker anymore. That's also why I know, just by the way, that this is the ice equation without the OH minus. All the OH is gone at this point, so we can't include it in the second equation. Okay, so I'm left with this equation. I would have 0.02 divided by 3 and lose X and add X over to here and add X over to here. The other trick that you have to know at letter E is that we would have x squared over 0.02 divide 0.3, and that is now equal to the KB, not to the KA. I know it's the KB because I have the OH minus here. To solve for the KB, you have KA times KB equals KW. You can look in the back of the book for your answer to this one. And lastly, after equivalence, we have 0.02 and 0.025, so we'll have leftover base. We also have some conjugate base on this side. And notice that the conjugate base actually has more moles than the OH minus itself. But the conjugate base is weak, so it's going to only have partial dissociation. This is a mixture at this point of a strong base and a weak base. And when you have a strong and a weak together, you remember from mixtures that we did, you can ignore anything coming from the weak and just take the number from the strong. And when we do that, we would get the pH is 12.15.